Okay, so let's continue. So basically, imagine these are two carbon nanotubes or carbon nanofibers, really doesn't matter. And the reason you see different curvatures is because imagine one of them is going like that through the board and the other one is like this. So we're looking at a cross section of them. And now the epsilons are strained. So it's biaxial strain, which could be uniaxial as well by setting one of them to Poisson ratio times the minus Poisson ratio times the other one. But as a result of this, so basically if I draw my composite, so basically this is my composite, and in it I have my carbon nanotubes or nanofibers which have percolated, and they're passing current from one end to the other. Now imagine I do one thing here. I apply a strain from this side, I go this way, and I go this way in the other side. As I'm loading this, the spacing between these carbon nanotubes, the spacing will slightly increase because, on average, because the volume of the material is going up when I'm applying tension. And if that is the case, then it means it's as if the total volume of carbon nanofibers or nanotubes hasn't changed. The total volume of the material has changed. So it's as if my average volume fraction has been reduced, okay? But the percolation threshold has remained the same. Basically, I still need, for instance, 1% of carbon nanofibers or carbon nanotubes to carry the load, to carry a strain, to carry electricity from one end to the other. But now the average distance between them goes up, which means it's as if I have less number of carbon nanofibers or carbon nanotubes per unit volume. And so if I was above the percolation threshold, which means I was conductive, now I'm moving towards the percolation threshold or perhaps below that. And so the resistivity of that can significantly go up. Now, the reason it can significantly go up is because of this exponential relationship, actually, between resistivities. That when the spacing goes up, when a strain is applied, when I apply a strain, the spacing changes. And because the resistivity is exponentially related to that, the resistivities of the whole sample significantly go up. So now, this is an example, this is an experiment that a few folks did. They put different concentrations of carbon nanotubes inside a matrix, and they measured resistivity, the change in resistivity as a function of a strain. So, and I hope you remember the equation we had for the resistivity, which was 1 plus 2 nu plus the derivative of rho with respect to rho epsilon. This was delta R over R epsilon, right? And so now the maximum value for the first term, which is primarily because of geometry, is what we call, the maximum value for that is 2. If a material is not piezo-resistive, this change has to be equal to 2. That's why in this graph, they plotted this line, or maybe I can show it with a different color. They plotted this line, which corresponds to the case where K is equal to 2. K is basically the ratio of delta R over epsilon. The relative change in resistance for a unit of a strain. So now, what is very important to consider is that actually in all cases you get much, much higher change in resistance. That's a very good thing because they can act like a sensor. the other thing that you have to keep in mind is that here, the piezoresistivity is mostly rooted in this term, is rooted in the change in this tunneling resistance between two carbon nanofibers or any two carbon nanofiber or any two carbon nanotube. And how do I know that? Well, I know it because this trend, the lower the volume fraction, the higher this change. And the lower the volume fraction, the very high volume fractions are somewhere here. As we reduce the volume fraction, we get closer to where basically the percolation threshold happened. And in this region, we are very sensitive to distances between carbon nanotubes or carbon nanofibers. We're very sensitive to the volume fraction. So even a slight changes in the volume fraction or slight changes in, which is equivalent to slight changes in the average spacing between carbon nanotubes, can result in a significant change. Just to put things in perspective to see so that you can appreciate the values here, let's take, for instance, this point. Oops. Let's take this point here, and or even maybe this point here. It's at 1% the strain, the case of the lowest volume fraction. And in this case, delta R over R is almost 0.7. That's 70%. So delta R over epsilon is actually 70 over 1. So so it's 70 basically, whereas only 1 plus 2 nu is what we can account for. The rest of it shows the significance of this term. And what would have happened if we had tested lower concentrations, 0.5 or 0.05? Well, those cases are below the percolation threshold. For those, the resistivity is super, 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 super high. It's practically, for all practical purposes, a non-conductive material. Now, we talked a lot about percolation threshold. Let's see if we can quantify that and understand that. A concept that comes to mind with, there's this paper here in 1984. It's a highly influential paper in which they define this concept of excluded volume. Imagine I have these two particles in a composite or in a nanocomposite. These could be carbon nanotubes or carbon nanofibers, graphene, whatever you want to have. This is first one. I randomly call one of them number 1. And I imagine the average angle between them, or the angle between them, is theta or gamma. It's different references use different terms. I put both of them here. Now, I can move this guy, number 2, around 1 in very different cases. I can put it here. I can put it here. I can, while maintaining the angle, I can put it here. I can put it here, 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 here. And in all these cases, all I'm trying to do is avoid 1 and 2 penetrating into each other, because penetration between nanofillers doesn't happen. So then I can define, this is an area, but in 3 dimensions, it will be a volume. I can define an area like this, which I call the excluded volume of particle 1. It's the volume around object 1 that an object 2 can appear to just touch object 2, but not penetrate object 2. So from basically simple geometry, if you have your particles are like that, basically cylinders with semi-spherical objects at each cap, you can easily calculate the volume of each rod. You can also calculate this excluded volume, basically the volume of this yellow thing. And they proved, or they demonstrated, that the percolation threshold will be the ratio of these two volumes. And it kind of makes sense if you think about it. Basically, it's the volume that the second object can be in as long as they're in contact with each other. So here in this assumption, the spacing between them is supposed to be 0, and not, basically we're not considering that exponential function. But if we add that, we can add this spacing and consider a higher excluded volume, which means that would correspond to a lower percolation threshold. I will continue in the next slide.